Tonight we're going to explore one of the most baffling puzzles in modern astrophysics. There are black holes out there in the distant universe that should not exist. They're too massive, too early, too impossible. Because physics sets a speed limit on how fast a black hole can eat. There's a boundary, a point where the radiation pouring off infalling matter should push everything away and shut down the feeding entirely. And yet, astronomers have found black holes that appear to be gorging themselves at 40 times that supposed limit, 40 times faster than the physics should permit. Something is breaking the rules, or maybe the rules were never what we thought they were. And what we're about to uncover doesn't just explain how black holes cheat. It might solve one of the biggest mysteries in the entire cosmos. Before we go any further, if you find this kind of deep dive into the universe interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems straightforward but hides enormous complexity. How does a black hole actually grow? Before we can answer that, we need to be clear about what a black hole actually is, because the reality is stranger than the popular image suggests. A black hole is what happens when gravity wins completely. When a massive star, one containing perhaps 20 or 30 or even 100 times the mass of our Sun, exhausts its nuclear fuel and can no longer support itself against its own weight, the core collapses. If the star is massive enough, nothing can stop the collapse. No force in nature is strong enough to resist. The matter keeps falling inward, compressing into a smaller and smaller volume until it reaches a point of essentially infinite density, at least according to our current understanding of physics. What's left behind is a region of space-time so warped, so curved by that concentrated mass that nothing can escape from it. Not matter, not radiation, not even light itself, the fastest thing in the universe. The boundary around a black hole from which nothing can return is called the event horizon. It's not a physical surface. You wouldn't feel yourself cross it. There's no wall, no barrier, no visible edge. It's simply the point of no return. Cross it, and no amount of energy, no engine, no force can bring you back. The event horizon is what makes a black hole black. Light generated inside the event horizon can never reach the outside universe. It's trapped forever, falling inward along with everything else. From outside, a black hole is defined entirely by what crosses that boundary. Everything that falls through the event horizon adds to the black hole's mass. Every photon, every atom, every grain of dust that crosses that invisible line makes the black hole slightly heavier and makes the event horizon slightly larger. And this is the key to our story tonight. Because if a black hole grows by accumulating mass through its event horizon, then the rate at which mass crosses that boundary determines how fast the black hole gets bigger. And it turns out there are powerful forces that try to prevent mass from getting there. You probably have a mental image of this process. A dark void hanging in space, pulling everything toward it like some cosmic drain. Matter falls in, the black hole gets bigger. End of story. And in the very broadest sense, that picture isn't entirely wrong. A black hole does attract nearby matter with its gravity, the same way any massive object does. But the actual process by which that matter reaches the black hole and adds to its mass is far more complicated, far more violent, and far more interesting than most people realize. Here's the first thing you need to understand. Matter almost never falls straight into a black hole. This surprises a lot of people because the popular image of a black hole is this irresistible vortex that swallows everything in its path. But space is big, and things in space are moving. Gas clouds drift, dust tumbles, stars orbit. Everything in the vicinity of a black hole has at least some sideways motion, some velocity that isn't aimed directly at the black hole's center. And when gravity begins pulling that material inward, that sideways motion doesn't disappear. Physics won't allow it. Angular momentum is conserved, and as the gas falls closer, that sideways motion doesn't shrink. It gets amplified. So instead of plunging straight in, the gas spirals. It swirls around the black hole, faster and faster, and as more material joins the flow, it flattens out into a vast rotating structure. Astronomers call this structure an accretion disk. And an accretion disk is one of the most extraordinary environments in the entire universe. Picture a disk of gas stretching millions or even billions of miles across, spinning around a black hole at speeds that can approach a significant fraction of the speed of light in its innermost regions. The gas in the inner part of the disk orbits faster than the gas farther out. These adjacent layers, moving at different speeds, rub against each other, creating friction. And that friction generates heat. Staggering heat. The inner regions of an accretion disk around a stellar mass black hole, one that formed from the death of a single massive star, can reach temperatures of tens of millions of degrees. Around a supermassive black hole, one containing millions or billions of times the mass of our Sun. The disk is physically much larger and the peak temperatures can be somewhat lower, but the total energy output is beyond anything you've ever encountered. At these temperatures, the gas doesn't just glow, it blazes. It radiates across the entire electromagnetic spectrum, from radio waves, through visible light, up through ultraviolet, and all the way to X-rays. In fact, some of the brightest objects ever observed in the universe are powered by accretion disks around supermassive black holes. These objects are called quasars, and a single quasar can outshine an entire galaxy containing hundreds of billions of stars. All of that light, all of that energy, pouring out of a region that's sometimes no larger than our solar system. It's an almost absurd concentration of power. And here's the crucial detail that makes this process so important for our story tonight. The energy released by accretion comes from gravity itself. As matter spirals deeper into the black hole's gravitational well, gravitational potential energy converts into thermal energy and radiation. And this process turns out to be remarkably efficient. A typical accretion disk around a black hole converts roughly 10% of the rest mass energy of the infalling material into radiation. 10% might not sound like much at first. But consider this comparison. Nuclear fusion, the process that powers every star in the night sky, the process that lights up our sun and makes life on Earth possible, converts only about 0.7% of mass into energy. Accretion onto a black hole is more than 14 times more efficient than that. Pound for pound, a black hole's accretion disk extracts more energy from matter than the core of any star. It's one of the most efficient energy sources that nature has ever devised. And this extraordinary efficiency creates something both remarkable and deeply problematic. All that radiation streaming outward from the accretion disk doesn't just passively illuminate the surrounding space, it pushes. Photons, the particles of light, carry momentum. When a photon strikes a particle of gas, it transfers a tiny amount of momentum, giving that gas particle a small outward kick. One photon, one tiny push, barely noticeable. But in the searing environment of an accretion disk producing incomprehensible amounts of light, those tiny pushes accumulate into an enormous outward force, and that force acts directly against the inward pull of gravity. This creates a fundamental tension at the heart of black hole growth. Gravity wants to pull gas in, radiation wants to push gas away. These two forces are locked in a tug of war, and the outcome of that tug of war determines how fast the black hole can feed. And this tension is what leads us to one of the most important concepts in all of astrophysics. A concept that was first discovered not in the context of black holes, but in the study of ordinary stars. In 1926, a British astrophysicist named Arthur Eddington published a landmark book called The Internal Constitution of the Stars. Eddington was wrestling with a puzzle that had occupied astronomers for decades. Why don't stars collapse? A star is an enormous ball of gas held together by its own gravity. That gravity is constantly trying to crush the star inward, to compress it into an ever smaller volume. Something must be fighting back. Something must be pushing outward, holding the star up, keeping it in balance. Eddington realized that radiation pressure was the key. Deep inside a star, nuclear fusion reactions produce enormous quantities of light. That light pushes outward against the surrounding gas, creating an outward pressure that opposes the inward pull of gravity. The star exists in a delicate equilibrium. Gravity pulls in, radiation pushes out. When these two forces balance, the star is stable. It neither collapses nor blows apart. It sits there, steadily burning its fuel and shining. But Eddington pressed the question further. He asked something deceptively simple. What happens if you keep making the star more luminous? What if the radiation output keeps climbing higher and higher? At some point, the outward radiation pressure must overpower the inward gravitational pull. When that happens, the outer layers of the star get blown away. There's a threshold, a maximum luminosity, above which radiation overwhelms gravity. Below that threshold, gravity holds material in place. Above it, radiation wins and gas escapes. This threshold is what we now call the Eddington luminosity, or more casually, the Eddington limit. Eddington derived it for stars, but the underlying principle applies everywhere gravity and radiation compete, including the gas swirling around a black hole. The calculation behind the Eddington limit is surprisingly elegant. You take a small parcel of gas near a luminous, massive object. You calculate the inward gravitational force pulling on that parcel. Then, you calculate the outward force that radiation exerts on the same parcel through a process called electron scattering, where photons bounce off free electrons in the ionized gas. You set these two forces equal and solve for the luminosity at which they exactly balance. The result depends on just two things: the mass of the central object and the opacity of the surrounding gas, which is essentially a measure of how effectively the gas interacts with passing radiation. For fully ionized hydrogen, the kind of gas you typically find around accreting black holes, the opacity is dominated by electron scattering, and in that case, the Eddington luminosity scales directly with mass. Double the mass of the black hole, and you double the Eddington luminosity. A black hole 10 times more massive has an Eddington luminosity 10 times higher. For a black hole with the mass of our Sun, the Eddington luminosity works out to roughly 33,000 times the total luminosity of the Sun. For a black hole containing 1 billion solar masses, the number climbs to about 33 trillion solar luminosities. These are enormous quantities of energy, but they function as ceilings, as boundaries. The standard picture held that if a black hole's accretion disk tried to shine brighter than this threshold, the outgoing radiation would push away the incoming gas, choking off the fuel supply and throttling the feeding back down. Now, here's where this connects directly to how fast a black hole can grow. If there's a maximum luminosity, and if that luminosity is powered by matter falling inward, then there must also be a maximum rate at which matter can fall in. You can work backward from the Eddington luminosity to calculate the corresponding maximum mass accretion rate. This depends on the radiative efficiency of the disk, the fraction of the infalling material's rest mass energy that gets converted into radiation rather than swallowed by the black hole. For a standard thin accretion disk, that efficiency is about 10%, meaning 90% of the mass actually crosses the event horizon and adds to the black hole, while 10% escapes as light. With these assumptions in hand, you can calculate something called the Salpeter time, named after astrophysicist Edwin Salpeter. The Salpeter time is the characteristic timescale for exponential growth. It tells you how long it takes for a black hole feeding continuously at exactly the Eddington rate to multiply its mass by a factor of roughly 2.7, which is 1 e-folding. For a thin disk with 10% radiative efficiency, the Salpeter time works out to approximately 45 million years. That number is the fundamental clock governing black hole growth in the standard picture. Every 45 million years of continuous Eddington rate feeding, the black hole's mass multiplies by about 2.7. Feed it for 100 million years, and the mass grows by about a factor of 9. Feed it for 500 million years, and the growth becomes dramatically exponential, multiplying the mass by a factor of roughly 65,000. Feed it for 800 million years, and you've multiplied the mass by more than 1 billion. The growth accelerates because as the black hole gets heavier, its Eddington luminosity rises, allowing it to consume gas at a higher absolute rate. It's a runaway process, but a controlled runaway, governed by a well-defined speed limit. For decades, this picture worked elegantly. The standard thin accretion disk model, developed in the early 1970s, described a disk that is geometrically thin, like a flat plate rather than a donut. In a thin disk, gas orbits the black hole in nearly circular paths. Friction slowly transfers angular momentum outward, allowing material to spiral gradually inward. The disk stays thin because radiation escapes efficiently from both the top and bottom surfaces. Photons are produced inside the disk and find their way out quickly. This efficient cooling prevents the disk from puffing up, and because the radiation escapes cleanly, it exerts its full outward pressure on any infalling gas, enforcing the Eddington limit in a self-consistent, self-regulating way. And astronomers had strong reasons to trust this picture because observations in the nearby universe confirmed it beautifully. When they studied X-ray binary systems in our own galaxy, compact objects feeding from companion stars, the luminosities they measured clustered at or below the Eddington limit for the inferred masses. The objects behaved exactly as the theory predicted. When they studied active galactic nuclei in relatively nearby galaxies, the relationships between black hole mass, luminosity, and accretion rate followed the Eddington framework with impressive consistency. The thin disk model predicted specific spectral shapes, specific temperature profiles across the disk, specific ratios between luminosity at different wavelengths. Observations matched those predictions time and time again. This consistency across different types of objects, across different mass scales, across different environments, built enormous confidence. The Eddington limit wasn't just a theoretical construct sitting on a page. It was a tested, validated, observationally confirmed boundary that appeared to govern real black holes in the real universe. Scientists had every reason to treat it as reliable, and for decades, they did. And then astronomers looked deeper into the universe, farther away in distance, and therefore, because light takes time to travel, farther back in time. And what they found shattered everything. It began as a trickle. In 2001, astronomers identified a quasar designated SDSSJ 1030 plus 05 24, shining at a redshift of 6.3. That placed it at a time when the universe was only about 870 million years old. The black hole powering it appeared to contain roughly 1 billion solar masses. That was already deeply uncomfortable. 1 billion solar masses assembled in under 900 million years required accretion at or near the Eddington limit, with essentially no interruptions. Tight, but technically possible. Barely. Then the discoveries accelerated. Each new survey peeled back another layer of cosmic time and found more black holes that were too heavy for their age. In 2011, astronomers announced the discovery of ULASJ 1120 plus 0641, a quasar at redshift 7.1. This black hole existed when the universe was just 770 million years old. Its estimated mass was roughly 2 billion solar masses. 2 billion. In 770 million years. The math was now straining. You could make it work on paper, but only by assuming a generous seed mass, perfectly continuous feeding, and not a single interruption in the gas supply over hundreds of millions of years. Every assumption had to break your way simultaneously. Remove any one of those favorable conditions, and the calculation failed. By the mid-2020s, telescopes had found dozens of quasars at these extreme redshifts, each one hosting a supermassive black hole that seemed to have no business existing so early. Some appeared at redshift above 7, corresponding to a universe younger than 750 million years. A handful pushed past redshift 7.5, squeezing the available growth time down to around 650 million years. And the masses weren't modest. Several exceeded 1 billion solar masses. Some appeared to exceed several billion. Each new discovery deepened the crisis. These weren't anomalies that could be explained away. They were a population, a pattern, a consistent signal from the early universe telling astronomers that something about their growth model was incomplete. Now let's run the numbers and feel the full weight of the problem. Imagine you start with a seed black hole formed from the collapse of one of the first generation of massive stars. Those early stars are thought to have been enormous, perhaps 50 to a few hundred times the mass of our Sun. When they died, some of them collapsed into black holes with masses of maybe 10 to 100 solar masses. Let's be generous. Let's say our seed starts at 100 solar masses. That's already a large seed, bigger than most stellar mass black holes we observe in the nearby universe. Now let's feed this seed at the maximum Eddington rate, continuously, with no interruptions whatsoever, using a standard thin disk with 10% radiative efficiency. The Salpeter time is 45 million years. To grow from 100 solar masses to 1 billion solar masses requires multiplying the mass by a factor of 10 million. That demands roughly 16 e-foldings. 16 times 45 million years gives about 720 million years. On the surface, that might seem like it barely works. 720 million years of growth, observed in a universe that was roughly 700 to 800 million years old. So in principle, just barely, you could get there. But only if every single assumption falls perfectly in your favor. And here is the problem. Every single assumption doesn't fall in your favor. First, the seed doesn't form the instant the Big Bang happens. The first stars didn't appear until roughly 100 to 200 million years after the Big Bang. Gas needed time to cool. Those stars needed time to live out their lives, burn through their fuel, and collapse into black holes. So you've already lost well over 100 million years from your time budget before the seed even exists. Second, continuous feeding at the Eddington rate for hundreds of millions of years without a single interruption is extremely unlikely. The environment around a young black hole is chaotic. Gas supplies fluctuate. Mergers with other galaxies disrupt the flow. The black hole's own radiation and outflows push gas away, periodically starving the black hole of fuel. Realistic computer simulations consistently show that black holes spend significant stretches of their lives in low accretion states, growing slowly or not at all. Some simulations find that black holes in early galaxies are actively accreting at high rates for only 20 to 40% of the available time. The rest of the time, they're idling, waiting for the next gas delivery. Assuming perfectly continuous Eddington rate feeding represents the most wildly optimistic scenario imaginable, and even that barely produces 1 billion solar masses in the time available. Cut the duty cycle to 50%, which is still optimistic, and the math fails outright. Third, the quasars discovered in the early universe aren't all sitting at exactly 1 billion solar masses. Some appear to contain several billion solar masses. A handful push toward 10 billion. Reaching those masses requires even more E-foldings, even more time that simply isn't there. Fourth, there's an additional complication that actually works against growth. If the black hole is spinning rapidly and extended accretion tends to spin black holes up, the radiative efficiency can climb well above 10%. For a maximally spinning black hole, it can reach as high as 30 or even 40%. Higher efficiency sounds like a good thing, but for growth, it's actually damaging. Higher efficiency means more of the infalling mass energy gets radiated away as light, and less of it actually crosses the event horizon to add to the black hole's mass. A spinning black hole at the Eddington limit shines brighter, but it grows more slowly than a non-spinning one at the same accretion rate. The very process of accretion makes the black hole harder to grow. So the math doesn't work. Not comfortably. Starting from a stellar mass seed and growing through standard Eddington limited thin disk accretion, you simply cannot build a billion solar mass black hole in the time the universe provides. The numbers are too tight. The assumptions are too generous. Something in the standard picture is wrong. This is the crisis sitting at the heart of early universe astrophysics. These black holes are too massive and they appeared too early. They shouldn't exist. Not because black holes themselves are impossible, but because the standard growth model, the one that worked beautifully for decades and matched every observation in the nearby universe, simply cannot account for them. So what is going on? There are really only 3 possibilities. Either the seeds were much larger than 100 solar masses, giving the black hole a massive head start that reduces the number of E-foldings required. Or the growth rate exceeded the Eddington limit, at least during some episodes, allowing the black hole to feed faster than the standard picture permits, or some combination of both, potentially alongside mergers between black holes, conspired to build these monsters in the limited time available. And this is where our journey takes a truly fascinating turn. Because as it turns out, the Eddington limit is not a fundamental law of physics. It is not etched into the fabric of space-time the way the speed of light is. It is not a conservation law like the conservation of energy. It is a calculation. A calculation built on a set of specific assumptions. Assumptions about geometry. Assumptions about how radiation interacts with matter. Assumptions about how the gas flows and how the accretion disk is structured. And when those assumptions break down, when the conditions around a feeding black hole become extreme enough, the Eddington limit can be exceeded. Sometimes by modest amounts, and sometimes, as we're about to discover, by staggering factors that nobody expected. The speed limit, it turns out, has loopholes, and those loopholes might be exactly what the universe exploited to build its most enormous black holes in record time. So we've reached a crisis. The standard picture of black hole growth, with its thin accretion disk and its clean Eddington limit, cannot explain what astronomers are finding in the early universe. Black holes that are too massive, appearing too soon, growing faster than the supposed speed limit allows. The math doesn't close. The time isn't there. But here's what makes this story truly fascinating. The solution doesn't require tearing up the laws of physics. It doesn't demand new particles, new forces, or some radical overhaul of general relativity. This solution was hiding in plain sight all along, buried inside the assumptions that the Eddington limit is built upon. Assumptions that seemed perfectly reasonable. Assumptions that worked beautifully for decades. But assumptions that, under extreme conditions, quietly fall apart. Let's go back to how the Eddington limit was derived and examine those assumptions one by one. Because when you look closely at each one, you start to see cracks. And when enough cracks appear, the whole ceiling gives way. The first assumption is spherical symmetry. When Arthur Eddington first calculated his luminosity limit, he was thinking about stars. Stars are roughly spherical. They radiate light outward in all directions more or less equally. Gravity pulls inward in all directions equally. So the balance between radiation pressure pushing out and gravity pulling in is the same everywhere around the star. This makes the calculation clean and elegant. You compare two forces, set them equal, and the maximum luminosity falls out naturally. But a black hole feeding from an accretion disk is not spherically symmetric, not even remotely. Gas doesn't rain in from all directions at once. It spirals through a flat disk, concentrated around the equatorial plane. The geometry is completely different from a sphere. In the inner regions near the black hole, if the feeding rate is high enough, the disk swells into something more like a donut, thick and bloated with trapped energy. But even then, the structure still has a clearly defined plane where most of the mass resides, and clearly defined poles where the gas column is thin and sparse. This asymmetry changes the entire tug-of-war between radiation and gravity. Along the equatorial plane, gas is thick and dense and flowing inward with tremendous momentum. Along the rotational poles, there's much less material. And radiation, like water flowing downhill, finds the path of least resistance. Think of it this way. Imagine you have a balloon full of water. If the balloon is perfectly spherical and you poke identical holes in it everywhere, the water leaks out equally in all directions. That's the Eddington picture. Uniform, symmetric, balanced everywhere. Now, imagine the balloon is shaped like a donut, thick around the middle and thin on top and bottom. If you pressurize the inside, the water doesn't push out equally in every direction. It bursts through the thin parts on top and bottom because those are the weakest points. The thick walls around the middle stay intact, containing the water despite the internal pressure. The pressure escapes where it's easiest to escape, and the material along the thick equatorial band stays put. This is essentially what happens around a rapidly feeding black hole. Radiation escapes preferentially along the poles where the gas column is thin and where there's relatively little material to push against. Meanwhile, along the equatorial plane where the disk is thick and opaque, the radiation can't punch through. There's simply too much gas in the way. So matter continues streaming inward through the equator, even while radiation blasts outward along the poles. You get powerful outflows in one direction and powerful inflows in another, happening simultaneously, not contradicting each other but coexisting in separate directions around the same object. The outflows handle the excess radiation energy. The disk continues feeding the black hole. This is fundamentally different from what the simple Eddington calculation describes. In that calculation, radiation pushes gas away in the same direction gas is trying to fall in. It's a head-on confrontation, and radiation eventually wins. But when the geometry isn't spherical, radiation and matter can avoid each other entirely. They use different pathways, different exits. The radiation leaves through the poles, the matter enters through the equator, and the black hole grows faster than Eddington ever imagined. The second assumption built into the Eddington framework concerns the structure of the accretion disk itself. The standard model assumes a thin disk. The foundational version of this model was developed in 1973 and quickly became one of the most successful theoretical tools in astrophysics. In a thin disk, gas radiates its energy efficiently. As gravitational energy converts into heat through friction between adjacent layers of the disk, that heat transforms into photons that escape cleanly from the top and bottom surfaces. The disk sheds energy nearly as fast as it generates it. It stays cool relative to how hot it could get, and that cooling keeps it geometrically slim. Think of a compact disk sitting flat on a table. Thin, flat, well-behaved. Everything is orderly. But this tidy picture depends on a crucial condition. The disk has to be able to radiate away its energy as fast as the energy is being generated. And that condition holds only if the accretion rate is at or below the Eddington rate. When the rate is modest, the energy balance works. Heat is produced, photons carry it away, the disk stays thin. But what happens when gas pours in faster? What if the fuel supply overwhelms the disk's ability to cool? What if energy is generated faster than photons can carry it away from the surfaces? The disk inflates, it puffs up, it swells vertically because the trapped energy heats the gas beyond the point where the disk's own gravity and pressure can keep it flat. Astronomers call this a slim disk, though the name is misleading because there's nothing slim about it. These disks can become geometrically thick, with a vertical height comparable to their radial extent, especially in the inner regions near the black hole. If a standard thin disk looks like a dinner plate, a slim disk looks more like a bagel, fat and swollen in its center. The concept was developed formally in the late 1980s, and it described a regime of accretion that the earlier thin disk model was never designed to handle. This geometric swelling has consequences that cascade through the entire physics of the accretion flow. A thick disk presents a fundamentally different environment for photons than a thin one does. In a thin disk, a photon generated somewhere inside the flow has a short distance to travel before it reaches the surface and escapes into space. The disk is slim. The walls are thin. Escape is easy and fast, but in a thick, bloated disk, that same photon faces a much longer and more tortuous journey. It has to diffuse outward through a vastly larger column of dense gas. And if the gas is thick enough and moving inward fast enough, those photons may never reach the surface at all. This is where we arrive at what is arguably the single most important loophole in the entire Eddington framework. A mechanism called photon trapping. Photon trapping sounds technical, but the core idea is intuitive once you see it. Here's how it works. In a very high accretion rate flow, the gas rushing toward the black hole is extremely dense. It's opaque, meaning photons can't travel freely through it. Instead of streaming outward in straight lines, photons bounce around inside the gas. They scatter off free electrons. They get redirected, deflected, sent on random walks through the medium. Each photon makes progress toward the surface only gradually, taking one tiny diffusive step at a time, bouncing its way outward through a maze of interactions. But here's the catch. While the photon is slowly diffusing outward, the gas itself is hurtling inward. The gas is falling toward the black hole under the relentless pull of gravity. And if the inward speed of the gas exceeds the outward diffusion speed of the photons lose the race. They get swept along with the flow, carried inward, dragged across the event horizon, and into the black hole itself. Let me give you an analogy that might make this vivid. Imagine you're standing on a moving walkway in an airport, the kind that carries you along a corridor automatically. Now, imagine you decide to walk backward against the direction the walkway is moving. If the walkway is slow, you can outpace it. You walk backward faster than it moves forward, and you gradually make progress against the flow. But now imagine someone cranks the speed of the walkway way up. It starts moving so fast that no matter how quickly you walk backward, you're still carried forward. Your legs are pumping, you're making effort, but the ground beneath you is moving faster than you can go. You're trapped on the walkway, heading in a direction you don't want to go, unable to escape. Photons in a super Eddington accretion flow are exactly like this. They're trying to diffuse outward, bouncing off electrons, making their slow, random walks toward the disk surface. But the river of gas they're embedded in is flowing inward faster than they can diffuse outward. The photons are trapped. They're carried into the black hole with the gas. And this changes everything about how the accretion process works. Because if the photons can't escape, they can't exert outward radiation pressure. The brake pedal is disconnected. The very mechanism that's supposed to enforce the Eddington limit, outward pushing photons opposing infalling gas, simply doesn't function. The photons that would create that outward pressure never get the chance to do their job. They're born inside the flow, trapped before they can push anything, and consumed by the black hole before they can regulate anything. The effect becomes more extreme the deeper into the flow you look. Near the outer edge of the disk, where the gas is less dense and the infall velocity is lower, photons can still escape. The Eddington limit still roughly applies out there. But in the inner regions, close to the black hole where gas is densest and falling fastest, photon trapping becomes utterly dominant. Virtually all the radiation generated in the innermost flow gets swallowed. It never reaches the disk surface. It never streams outward. It never pushes against a single atom of infalling gas. This creates a remarkable situation. The black hole can consume gas at a rate far exceeding the Eddington prediction, because the radiation that should be enforcing that prediction has been silenced. The energy is still being generated. Gravitational potential energy still converts into heat and photons deep inside the flow. But those photons are impotent. They never escape. They never oppose the inflow. They simply get eaten along with everything else. And this isn't a subtle effect. It's dramatic. Theoretical models show that when gas is supplied at 10 or 20 or even 100 times the Eddington rate, a significant fraction of the generated radiation gets trapped and swallowed. The effective radiation pressure drops far below what the simple Eddington calculation would predict. The ceiling lifts, and the black hole feeds at rates that would have seemed physically impossible just decades ago. Of course, not all the radiation is trapped. Some photons do escape, particularly along those polar directions where the gas column is thinnest. The combination of photon trapping in the dense equatorial regions and radiation escape along the sparse polar regions creates a distinctive two-zone picture. In the equatorial plane, the flow is dense, opaque, inward rushing. Photons are trapped. Accretion proceeds at super Eddington rates. Along the polar axes, radiation streams outward through the funnel, created by the thick inner disk. This escaping radiation can be intense, sometimes appearing well above the Eddington luminosity if you happen to be looking directly down the funnel. And that leads us to something critically important that's deceptively easy to overlook. There is a fundamental distinction between the rate at which a black hole is actually consuming mass and the luminosity that astronomers observe from a distance. These two quantities are not the same thing. And in super Eddington flows, the gap between them can be enormous. In the standard thin disk model, accretion rate and luminosity are tightly linked. About 10% of the infalling rest mass energy converts to radiation that escapes. So if you measure the luminosity, you can calculate backward to get the accretion rate. The relationship is clean, predictable, and reliable. In a super Eddington flow with photon trapping, this relationship falls apart completely. The actual mass reaching the black hole can be vastly higher than what the luminosity suggests, because most of the generated radiation never escapes. It's trapped and swallowed. The luminosity you observe from outside is only a fraction, sometimes a small fraction, of what the accretion rate would produce in a standard thin disk scenario. The black hole is eating far, far more than its light output implies. There's an additional complication that makes interpretation even harder. The luminosity you observe depends on your viewing angle. If you're looking face-on down the polar funnel, straight into the channel where radiation escapes most efficiently, the source appears extremely bright. You might measure a luminosity that exceeds the Eddington value and conclude the black hole is accreting at many times its Eddington rate. But if you're looking edge-on, peering through the thick equatorial disk, the source appears much fainter. The dense gas absorbs and scatters the radiation before it reaches you. The same black hole, accreting at the same rate, looks completely different depending on where you're standing. One observer sees a blazingly bright quasar. Another observer, viewing the same object from a different angle, might see a much more modest source. Both are correct about what they see. Neither has the full picture. This viewing angle dependence has implications that go far beyond just measurement uncertainty. It may have been shaping how astronomers classify entire categories of cosmic objects for decades without anyone fully realizing it. Since the 1980s, astronomers have recognized that the universe contains many different-looking types of active galaxies, brilliant quasars visible across billions of light years, Seyfert galaxies with bright but less extreme cores, radio galaxies with powerful jets but relatively dim centers, blazars that vary wildly in brightness over days or weeks. These objects look so different from each other that for years they were studied as entirely separate phenomena, described in separate papers, catalogued in separate databases, explained by separate theoretical models. But gradually, a radical idea took hold. What if these weren't different objects at all? What if they were the same kind of object? A supermassive black hole feeding through an accretion disk, viewed from different angles. Look down the polar funnel and you see a blazar, with radiation beamed directly at you, overwhelming and variable. Look from the side and you see a Seyfert galaxy, the bright core partially obscured by the disk. Look edge-on through the thick equatorial torus, and you see only the faint reflected glow of an obscured nucleus. Same engine, same physics, completely different appearance. This idea, known as the unified model of active galactic nuclei, has become one of the central organizing principles of extragalactic astronomy, and it connects directly to our story about super Eddington accretion, because the same geometric principle is at work. The appearance of an accreting black hole depends profoundly on where you're standing when you look at it. A super Eddington accretor viewed pole-on might appear as a spectacularly bright source with an inferred Eddington ratio of 40 or more. The same object viewed from the equatorial plane might appear as a modestly luminous or even heavily obscured source that nobody would flag as super Eddington at all. Orientation isn't just a nuisance for measurement. It fundamentally determines what kind of object astronomers think they're looking at. And this means that our census of super Eddington accretors in the universe, both nearby and in the early cosmos, could be dramatically incomplete. There's yet another piece of this puzzle that adds further complexity. The powerful outflows generated by super Eddington accretion carry away not just radiation but also mass. When radiation blasts out along the polar directions, it drives winds and jets of ionized gas. These outflows are not gentle or subtle. They're some of the most powerful phenomena in the entire universe. The winds launched from super Eddington accretion flows can reach velocities of several thousand kilometers per second. In the most extreme cases, these outflows have been measured at 10 or even 20% of the speed of light. At these velocities, the kinetic energy carried by the outflowing gas is enormous. A single outflow episode can carry more energy than our sun will produce over its entire 10 billion year lifetime, released not over billions of years but over mere millions. These winds slam into the surrounding gas of the host galaxy with devastating force, sweeping material outward, heating it, ionizing it, and sometimes driving it entirely out of the galaxy. Jets, the narrow beams of matter and energy launched from the poles of the accretion system, can be even more extreme. Some jets extend for hundreds of thousands of light years, far beyond the galaxy that produced them, plowing through the intergalactic medium and depositing energy at staggering distances from the black hole. These jets are visible across the electromagnetic spectrum, from radio waves to X-rays, and they represent one of the most efficient ways that a black hole transfers energy to its large-scale environment. You might think, All this ejected material would undermine the whole idea of super Eddington growth. If you're blowing gas away in outflows, aren't you losing the very material you're trying to accrete? And the answer is yes, partially. Not all the gas that enters the accretion flow reaches the black hole. A fraction, sometimes a substantial fraction, gets launched in outflows and lost. But the critical insight is this. Even after subtracting the mass lost in outflows, the net accretion rate, the mass that actually crosses the event horizon, can still greatly exceed the Eddington rate. Think of it like drinking from a fire hose. The water is coming in so fast that most of it sprays everywhere. It soaks your clothes. It blasts past your face. It drenches everything around you. The overflow is enormous, but the amount of water you actually swallow per second is still far greater than what you could drink from a glass. The overflow doesn't mean you're drinking slowly. It means the supply is so overwhelming that even the fraction you manage to consume is enormous compared to normal. The outflows are a consequence of super Eddington feeding, not a solution to it. They're a symptom of excess, not a cure. Computer simulations over the past 2 decades have confirmed this entire picture in stunning detail. And it's worth pausing to appreciate what these simulations actually involve, because they represent some of the most ambitious computational physics ever attempted. The challenge is enormous. You need to track the motion of gas in 3 dimensions around a black hole, accounting for gravity, fluid dynamics, pressure, and rotation. You also need to follow the behavior of magnetic fields that thread through the gas, twisting and amplifying as the disk rotates. These magnetic fields are crucial because they're responsible for the friction that drives accretion in the first place. Without magnetic turbulence, there would be no way for gas to lose angular momentum and spiral inward. Then, on top of all that, you need to track the radiation, the photons being generated, absorbed, scattered, and trapped within the dense flow. Radiation interacts with the gas, pushing on it, heating it, being carried by it. All of these processes happen simultaneously and influence each other in complex ways. The numerical codes that solve these problems are called radiation magnetohydrodynamic simulations. They divide the space around the black hole into millions of tiny computational cells. In each cell, at each moment in time, the code calculates the density, temperature, velocity, magnetic field strength, and radiation intensity. Then it advances the simulation forward by a tiny time step, recalculates everything, and repeats millions of time steps, millions of cells, trillions of individual calculations. A single simulation run can consume millions of processor hours on some of the most powerful supercomputers in the world. And the results have been remarkable. When researchers supply gas to a simulated black hole at rates well above the Eddington rate, the flow organizes itself naturally into exactly the structure we've been describing. Nobody programs in a thick disk. Nobody forces the polar funnels to form. Nobody tells the simulation to trap photons. All of these features emerge spontaneously from the physics. The disk inflates because the trapped energy forces it to. The polar funnels open because radiation seeks the path of least resistance. Photon trapping occurs because the gas is dense enough and fast enough to drag photons inward. The outflows launch because the escaped radiation pushes material off the funnel walls. It all happens on its own, a self-organizing structure arising from the interplay of gravity, magnetism, and radiation under extreme conditions. The simulations reveal an important quantitative feature as well. The total luminosity of these flows doesn't increase proportionally with the accretion rate the way it does in a thin disk. In the thin disk regime, doubling the accretion rate roughly doubles the luminosity. But in the super Eddington regime, the relationship flattens out dramatically. Increasing the accretion rate by a factor of 10 might only increase the observed luminosity by a factor of 2 or 3. The rest of the generated energy is trapped and swallowed. The relationship between luminosity and accretion rate becomes logarithmic rather than linear. The light output crawls upward while the mass consumption soars. This has a profound practical implication. It means a black hole can be growing very rapidly while appearing only modestly bright. Its true growth rate is hidden, masked by photon trapping. The light reaching our telescopes is a poor indicator of the actual feeding frenzy happening near the event horizon. And this means there could be supermassive black holes in the early universe that were growing explosively, and we simply couldn't tell from their luminosity alone. So let's step back and look at the full picture we've assembled. The Eddington limit, which seemed for decades like a firm and universal ceiling on black hole growth, turns out to be a calculation built on specific assumptions about geometry, disk structure, and radiation transport. When the accretion rate climbs high enough, the disk inflates. Photons get trapped inside the dense flow and swept across the event horizon. Radiation that does escape takes the path of least resistance through the poles, rather than opposing the equatorial infall. Powerful outflows develop, carrying mass and energy at tremendous velocities, but net accretion still exceeds the classical limit. The observed luminosity may wildly misrepresent the true rate at which the black hole is gaining mass. And the very appearance of the accreting system, what kind of object astronomers classify it as, depends on the angle from which it happens to be observed. None of this violates any law of physics. Energy is still conserved. General relativity still governs space-time around the black hole. Photons still move at the speed of light. What changes is the specific balance between radiation pressure and gravity, and that balance depends on conditions that the simple Eddington calculation never accounted for. The Eddington limit isn't wrong, it's just incomplete. It describes what happens under idealized conditions, the thin disk regime, where everything is neat and orderly. But when conditions become extreme enough, the idealization fails. And when it fails, the limit can be breached, sometimes modestly, sometimes spectacularly. And theory, no matter how elegant, ultimately demands observational support. The question isn't just whether super Eddington accretion is physically possible. The question is whether the universe actually uses this loophole. Whether we can catch a black hole in the act of feeding beyond the limit. For years, the evidence was indirect. Astronomers saw ancient black holes that were too heavy for their ages and reasoned that super Eddington episodes must have occurred somewhere in the past. But catching one in the act, observing a black hole, gorging itself at rates that shatter the classical ceiling in real time, that proved elusive. Until recently, when a small but astonishing black hole in the early universe gave astronomers exactly what they had been searching for. For years, astronomers knew the loopholes existed in theory. The physics of photon trapping, thick disks, and directional radiation escape had been worked out on paper and confirmed in computer simulations. The math was sound. The mechanisms were plausible. But science demands more than plausible mechanisms. It demands evidence. Catching a black hole in the act of gorging itself at rates far beyond the Eddington ceiling seeing the physics actually play out in the real universe rather than in equations and supercomputer outputs, that remained the missing piece. Theorists could describe what super Eddington accretion should look like. Observers needed to find it. And then, in the early universe, they found exactly what they were looking for. A peculiar X-ray source called LID 568. The story of LID 568 begins not with a dramatic single discovery, but with the painstaking accumulation of data across multiple telescopes and surveys spanning years of observations. This object sits in a patch of sky that has been studied extensively by astronomers searching for active galactic nuclei, the brilliant cores of galaxies powered by accreting black holes. It was identified through deep X-ray surveys, the kind that use orbiting observatories to stare at small regions of the sky for extended periods, collecting X-ray photons one by one over hundreds of thousands of seconds of exposure time. Understanding why X-rays matter so much here requires appreciating what different types of light reveal about an accreting black hole. The accretion disk is not a uniform structure. It has layers, zones, regions of different temperature and density. The outermost parts of the disk, farthest from the black hole, are relatively cool. They glow at optical and infrared wavelengths. Moving inward, the disk gets hotter and the emission shifts to ultraviolet light. But the innermost regions, the zone closest to the event horizon where gas spirals at its fastest and friction generates the most heat, that region blazes at X-ray wavelengths. X-rays are the fingerprints of the most extreme accretion. They trace the heart of the engine, the region where matter makes its final plunge. If you want to understand how aggressively a black hole is feeding, X-rays are the wavelength to watch. The deep surveys that identified LID 568 accumulated X-ray observations over many individual observing campaigns, sometimes spanning years. Each session added more photons to the total, building up a picture like a photograph emerging slowly in a dark room. When enough photons accumulated, the source revealed itself. A faint but persistent X-ray glow coming from a specific location in the sky. But identifying an X-ray source is only the beginning. To understand what you're looking at, you need context. You need to know how far away it is, what kind of galaxy hosts it, how luminous it truly is rather than how luminous it appears. And answering those questions requires observations at other wavelengths. Follow-up observations at optical and infrared wavelengths were essential. These observations revealed the host galaxy and, critically, established the cosmological redshift of the object. Redshift tells you how much the universe has expanded since the light was emitted, which in turn tells you how far away the source is and how long its light has been traveling. For LID 568, the redshift placed it firmly in the early universe at a cosmic time when the universe was still relatively young. The galaxy hosting this black hole was not one of the luminous monsters that typically grab headlines. It was comparatively modest. And the black hole at its center was also modest, at least in terms of mass. Initial estimates placed it at roughly a few million solar masses. That's a supermassive black hole by definition, far heavier than any star, but it's actually quite small by supermassive black hole standards. For comparison, the black hole at the center of our own Milky Way, Sagittarius E star, contains about 4 million solar masses, and many of the quasar black holes observed in the early universe contain hundreds of millions or even billions. LID 568 was small, but it was doing something extraordinary. When astronomers combined their measurements of the object's luminosity across multiple wavelengths, they undertook a process that's more art than it might seem from the outside. You don't just add the numbers together. You have to correct for the absorption of light by gas and dust, both in the host galaxy and along the line of sight between the source and Earth. You have to account for the cosmological redshift, which stretches the emitted light to longer wavelengths, shifting X-rays into softer X-rays and ultraviolet into optical. You have to apply models that estimate how much energy the source is emitting at wavelengths your telescopes didn't observe directly. The result of all this careful work is the bolometric luminosity, the total energy output across all wavelengths. And when that bolometric luminosity was compared to the estimated mass of the black hole, the number that fell out was extraordinary. The inferred accretion rate came back at roughly 40 times the Eddington limit. 40 times. Not twice, not 5 times, not even 10 times. 40. The reaction in the astronomical community was immediate and intense. This was precisely the kind of result that theorists had predicted was possible, but that observers had struggled to find. A real, observed black hole sitting in the real universe, apparently feeding at a rate that the classical Eddington framework said should be impossible. The fact that it was a relatively small black hole made the result even more striking. This wasn't a billion solar mass monster with enough gravitational brute force to overpower its own radiation. It was a comparatively lightweight object, gorging itself with an intensity that seemed out of all proportion to its size. But science, especially when confronted with extraordinary claims, demands extraordinary scrutiny. And the evidence for LID 568, while compelling, comes wrapped in layers of uncertainty that we need to examine carefully. Let's start with the most fundamental question. How do you measure how fast a distant black hole is eating? You can't see the gas falling in directly. You can't watch matter crossing the event horizon. What you can do is measure the light. You measure the brightness of the source at different wavelengths. Build up a picture of the total energy output, and then connect that luminosity to an accretion rate using physical models. But every step in this chain introduces assumptions and uncertainties. The first major uncertainty is the black hole's mass. The mass estimate for LID 568 relies on indirect methods. Astronomers don't weigh distant black holes on a scale. They infer the mass from properties of the light emitted by gas near the black hole. In many cases, they use the widths of emission lines, the bright spectral features produced by fast-moving gas in the vicinity of the black hole. The broader the line, the faster the gas is moving. The faster the gas is moving, the stronger the gravitational field it's orbiting in, and therefore the more massive the central black hole. This technique is well established, but it carries uncertainties of a factor of 2 or 3 in either direction. A black hole estimated at 5 million solar masses might actually be 2 million or 15 million. That range matters enormously because the Eddington limit scales directly with mass. If the true mass is higher than the estimate, the actual Eddington ratio drops. A black hole estimated to be feeding at 40 times its limit might only be feeding at 15 or 20 times if the mass turns out to be on the higher end. Still impressive. Still super Eddington. But not as extreme. The second major uncertainty involves the bolometric luminosity itself. Astronomers don't observe the total luminosity directly. They measure the brightness in specific wavelength bands, X-rays from one telescope, optical light from another, infrared from a third, and then apply what's called a bolometric correction. This correction essentially fills in the gaps, estimating how much energy is being emitted at wavelengths they didn't directly observe. Bolometric corrections are derived from models and from observations of similar objects at lower redshifts where the data is more complete, but they're not exact. Different correction methods can give significantly different results. A factor of 2 uncertainty in the bolometric luminosity is not uncommon. The third uncertainty is geometric, and this is where the super Eddington physics we discussed earlier becomes critically relevant. We established that a super Eddington accretor doesn't radiate equally in all directions. Radiation escapes preferentially along the polar funnel, while the equatorial regions remain opaque. If we happen to be viewing LED 568 from a nearly face-on orientation, looking straight down the polar funnel, the apparent luminosity could be significantly boosted relative to what an observer at a random angle would see. The true average luminosity might be lower than what we measure. This geometric beaming, as it's called, could inflate the apparent Eddington ratio. A black hole that's genuinely feeding at, say, 10 or 15 times the Eddington limit might appear to be feeding at 40 times if we're looking straight down the radiation chimney. On the other hand, this geometric effect cuts both ways. For every object like LED 568 that we observe face-on, and thus with amplified apparent luminosity, there should be many more similar objects viewed from less favourable angles that appear much fainter and slip below our detection thresholds entirely. The objects we do catch might be the tip of an iceberg. There could be an entire population of super Eddington black holes in the early universe that we've been missing simply because we're not looking at them from the right direction. The ones we do find might actually underrepresent how common super Eddington feeding really was. There's also the question of what exactly we're calling the accretion rate. In a standard thin disk, the relationship between luminosity and mass accretion rate is straightforward. 10% of the infalling rest mass energy comes out as light. You measure the light, you deduce the accretion rate. But in a super Eddington flow, this relationship breaks down because of photon trapping. Much of the generated radiation gets swallowed rather than escaping. So the observed luminosity underestimates the true accretion rate. When astronomers report that LID 568 is accreting at 40 times the Eddington limit, they're typically deriving this from the observed luminosity using standard thin disk assumptions. If photon trapping is significant, the actual mass falling into the black hole per unit time might be even higher than 40 times the Eddington rate. The radiation we see represents only the fraction that managed to escape. The honest answer is that the number 40 should be treated as an approximate indicator rather than a precise measurement. It tells us that something extreme is happening, that this black hole is feeding at a rate dramatically above what the classical Eddington picture permits. Whether the precise factor is 25 or 40 or 60 depends on modelling details that the current data cannot fully resolve. What matters is the order of magnitude. This isn't a black hole gently nudging past the limit by 20 or 30%. It's blowing past the limit by at least an order of magnitude, possibly more. And that's what makes it scientifically revolutionary. But here's what's truly important, and it's easy to miss amid all the discussion of uncertainties. Even the most conservative interpretation of the data for LED 568 represents a landmark result. even if the mass is at the high end of its uncertainty range, even if the bolometric correction is slightly too generous, even if geometric beaming is inflating the apparent luminosity by a factor of 2 or 3, even after all those corrections are stacked in the most conservative direction possible, the accretion rate still comes out well above the Eddington limit. Maybe not 40 times, maybe 10 or 15, but 10 times the Eddington limit is still extraordinary. It still validates the entire theoretical framework that was built across decades of work on photon trapping, thick disks, and geometric radiation escape. It still confirms that the Eddington limit, in its classical form, does not describe what happens under extreme conditions in the real universe. Think about what this means for the physics we explored earlier. If LID 568 is genuinely accreting at even 10 times its Eddington rate, that tells us the accretion flow around this black hole looks nothing like a standard thin disk. The disk must be geometrically thick, puffed up by trapped energy, with a vertical structure more like a swollen donut than a flat plate. Photon trapping must be operating in the dense inner regions, carrying radiation inward with the gas before it can escape to push anything outward. Radiation must be finding its way out primarily through the polar funnels, streaming along the path of least resistance through the low-density zones above and below the bloated disk, and powerful outflows must be present, driven by the fraction of radiation that does escape, carrying mass and energy away from the polar regions at high velocity. All of those mechanisms, every single one of the loopholes we discussed, must be at work simultaneously in LID 568. This object isn't just confirming a theoretical prediction, it's demonstrating that the universe actually builds these exotic accretion structures, that the physics of super Eddington feeding isn't just mathematically possible, but physically realized. Somewhere in the early universe, around a black hole containing just a few million solar masses, all of these mechanisms came together to produce a feeding frenzy that defied the classical ceiling by an order of magnitude or more. Theory met observation, and the theory held. Now, an important question follows naturally from all of this. Can a black hole sustain super Eddington feeding indefinitely? Can it just keep gorging at 40 times the limit for millions or hundreds of millions of years? Almost certainly not. And understanding why is crucial for building a realistic picture of how early universe black holes actually grew. Super Eddington accretion requires a massive and sustained fuel supply. The black hole needs an enormous reservoir of gas in its immediate vicinity. Gas that's able to lose enough angular momentum to spiral inward at the required rate. And maintaining that fuel supply for extended periods is extremely difficult in the chaotic environment of a young galaxy. Consider what's happening in the galaxy hosting LID 568. Gas from the surrounding environment is flowing toward the center of the galaxy. Maybe a merger with another galaxy is driving gas inward. Maybe the galaxy is embedded in a stream of cool gas flowing along a filament of the cosmic web. Whatever the mechanism, large quantities of gas are accumulating near the central black hole. This triggers a burst of intense feeding. The accretion rate skyrockets. The black hole enters a super Eddington phase. But this very process generates enormous energy output. And that energy doesn't just disappear. It floods outward into the surrounding galaxy through multiple channels simultaneously. The radiation escaping along the polar funnels carries tremendous power. The bipolar outflows, jets and winds driven by radiation pressure slam into the surrounding interstellar gas at thousands of kilometers per second. These winds are not gentle breezes. They're hurricane-force blasts of ionized material that can sweep through the galaxy's central region like a firestorm. When these outflows strike the gas reservoir that was feeding the black hole, the effects are devastating for future accretion. The outflows heat the gas. Cold gas can collapse and flow inward. Hot gas resists compression. It expands. It disperses. It becomes far harder for gravity to corral it back toward the black hole. The outflows also physically push gas outward, driving it away from the central region, and sometimes expelling it from the galaxy entirely. Computer simulations show that a single vigorous super Eddington episode can clear the gas from the black hole's vicinity for millions of years. The cupboard gets emptied, the fuel supply gets disrupted, and the accretion rate plummets. Astronomers call this process feedback, and it operates on multiple scales simultaneously. On the smallest scales, radiation pressure from the innermost disk pushes on gas just outside the accretion flow, creating a local bubble of hot, diffuse material that's difficult for new gas to penetrate. On intermediate scales, the outflows and winds sweep through the galaxy's central region, heating and dispersing the gas reservoirs that feed the disk. On the larger scales, jets can deposit energy hundreds of thousands of light years from the galaxy, heating the surrounding intergalactic gas and preventing it from cooling and flowing back inward. The result is a self-regulating cycle. The black hole feeds intensely, generates enormous feedback energy, disrupts its own fuel supply, and then starves. It enters a quiet period during which the gas slowly cools, settles, and begins flowing inward again. Eventually, enough gas accumulates to trigger another burst. The cycle repeats, perhaps triggered by another galaxy merger or another cold gas inflow event. So, super Eddington episodes are almost certainly temporary. They're bursts, flares of extreme activity that might last a few million years, perhaps 10 or 20 million years, before feedback effects choke off the gas supply and the accretion rate drops back down. This episodic picture changes the growth calculation significantly. The black hole doesn't feed continuously at 40 times the Eddington rate for hundreds of millions of years. Instead, it goes through repeated cycles, a burst of super Eddington feeding lasting a few million years, then a quieter period where the accretion rate drops, maybe to near the Eddington value, maybe lower. Then another burst when conditions align again. The time average growth rate is lower than the peak super Eddington rate, but still substantially higher than what the standard Eddington limited picture predicts. Even brief episodes of extreme feeding, if they're extreme enough, can dramatically accelerate the growth of a black hole over cosmic time. Let's put some rough numbers on this to see why it matters. Suppose a black hole spends 80% of its time in a low accretion state, feeding at roughly 10% of the Eddington rate or even lower. Growth during these quiet periods is minimal, but suppose it spends 20% of its time in super Eddington bursts at, say, 10 times the Eddington rate. Even though those bursts are relatively brief, they dominate the total growth. Most of the mass the black hole gains over its lifetime accumulates during those short, intense episodes. The quiet periods contribute almost nothing. It's like a snake that eats rarely but consumes enormous meals when it does. Most of its caloric intake comes from a handful of feeding events, not from steady grazing. If the bursts are extreme enough, reaching factors of 20 or 40 times the Eddington limit, the growth during those episodes can be explosive. A few million years of super Eddington feeding at 40 times the limit can accomplish what would take hundreds of millions of years at the standard Eddington rate. And that's exactly the kind of shortcut the early universe needs to produce billion solar mass black holes before the cosmos is a billion years old. LED 568 isn't the only object hinting at super Eddington feeding in the early universe, though it's among the most dramatic examples discovered so far. Over the past several years, astronomers have identified a growing population of active black holes in the first 1 to 2 billion years of cosmic history that appear to be accreting at rates above the Eddington limit. And several of these objects tell their own compelling stories. A class of objects known as narrow-line Seyfert-1 galaxies has long been suspected of harboring super Eddington accretors. These galaxies contain relatively low-mass black holes, often just a few million solar masses, that appear to be accreting at rates near or above their Eddington limits. Their X-ray spectra show distinctive features, rapid variability, steep spectral slopes, and strong soft X-ray emission that are consistent with the signatures expected from thick, radiation-dominated accretion flows. While most studied examples sit in the nearby universe rather than at high redshift, they demonstrate that super Eddington accretion is not confined to a single exotic object. It's a mode of feeding that nature uses repeatedly under the right conditions. At higher redshifts, deep surveys have uncovered growing numbers of active galactic nuclei with Eddington ratios exceeding 1. Some of these objects sit at ratios of 3 to 5, modest exceedances that might be explained by mildly super Eddington slim disk accretion. Others push toward 10 or beyond, entering the regime where photon trapping and geometric effects become dominant. The population is diverse, the accretion rates span a range, but the overall trend is clear. Super Eddington feeding was more common in the early universe when gas was abundant and galaxy mergers were frequent. Deep X-ray surveys have been particularly fruitful in uncovering these objects because X-ray emission traces the innermost accretion flow, the region where super Eddington effects are most pronounced. And the James Webb Space Telescope has added an entirely new dimension to this search. By observing in infrared wavelengths with unprecedented sensitivity and resolution, the James Webb Space Telescope can detect the faint host galaxies of these early black holes. It can measure the properties of the gas around them. It can reveal black holes in galaxies so young and distant that previous telescopes couldn't see them at all. Some of the galaxies discovered by the James Webb Space Telescope in its first years of operation contain black holes that are surprisingly massive relative to their host galaxies. In the nearby universe, astronomers have observed a well-established relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. Bigger galaxies tend to host bigger black holes. The ratio is roughly predictable, but several early universe galaxies spotted by the James Webb Space Telescope seem to have black holes that are too heavy for their galaxies. The black holes appear to have grown faster than their host galaxies, suggesting that rapid, possibly super Eddington accretion may have been more common in the early universe than anyone anticipated. This makes physical sense. The early universe was a denser place. Galaxies were closer together. Gas was more abundant. Mergers were more frequent. The conditions that enable super Eddington feeding, large amounts of gas flowing towards a central black hole, were much more easily achieved in the crowded, chaotic environment of the young cosmos. As the universe expanded and galaxies spread apart, as gas supplies dwindled and galaxies settled into more stable configurations, the opportunities for super Eddington bursts likely became rarer. The era of extreme feeding may have been a phase that the universe passed through during its youth, a brief adolescent growth spurt before things calmed down. There's a deeper insight embedded in the story of LID 568 and objects like it. These discoveries are not just about one particular black hole or one particular galaxy. They're about the mechanisms that built the large-scale structure of the universe we see today. Every massive galaxy in the present-day universe hosts a supermassive black hole at its center. The Milky Way has one. Andromeda has one. Every giant elliptical galaxy in every galaxy cluster, they all have one. These black holes didn't appear from nowhere. They grew. They started small and became large. And understanding how they grew, how fast they grew, and what physical processes enabled that growth tells us something fundamental about how galaxies themselves formed and evolved. Because black holes don't grow in isolation, they grow inside galaxies. And the energy they release during their growth, the radiation, the outflows, the jets, feeds back into the galaxy, shaping its evolution. A black hole going through a super Eddington episode doesn't just get heavier. It pumps enormous quantities of energy into its surroundings. That energy can heat gas and prevent it from forming stars. It can drive gas out of the galaxy entirely. It can regulate the overall rate of star formation across the entire galaxy for millions of years. This feedback loop between black hole growth and galaxy evolution is one of the most important processes in astrophysics. And super Eddington episodes, brief as they may be, represent the most energetic phases of this feedback. They're the moments when the black hole is loudest, when its impact on its host galaxy is most dramatic. The feedback from a single super Eddington burst can alter the star formation history of an entire galaxy, suppressing the birth of new stars for tens of millions of years until the gas reservoir can recover. Understanding objects like LID 568 helps us understand not just black holes, but the galaxies that contain them, and ultimately the universe as a whole. But even with super Eddington accretion providing a mechanism for rapid growth, the full story of how the earliest supermassive black holes came to be involves more than just feeding rate. There's another crucial variable we haven't fully explored yet. The starting point. How massive were these black holes when they began? Because the starting mass, the seed, determines how much subsequent growth is needed. A black hole that starts at 100 solar masses needs to multiply its mass by 10 million to reach a billion. But a black hole that starts at 100,000 solar masses only needs to multiply by 10,000. And a black hole that starts at 1 million solar masses needs only a factor of 1,000. The seed mass question is deeply connected to the super Eddington feeding question. They're two sides of the same coin. A heavier seed requires less extreme feeding to reach a given final mass. A lighter seed requires more extreme feeding, or more time, or both. The most complete explanation for the earliest supermassive black holes almost certainly involves both. Seeds that are heavier than the simple stellar collapse picture predicts, combined with episodes of super Eddington accretion that accelerate growth beyond the classical limit. And there's a third ingredient as well, one we haven't discussed yet, but that plays a crucial role in the full growth story. Mergers. Black holes can grow not just by eating gas, but by colliding and merging with other black holes. When two galaxies merge, their central black holes eventually spiral together and combine, instantly doubling or tripling their mass without a single gram of gas needing to fall in. These mergers are confirmed by gravitational wave observations. We've detected the ripples in space-time produced when black holes collide. Understanding how seeds, super Eddington feeding, and mergers work together across billions of years of cosmic evolution is the final piece of this puzzle. And it's where we're heading next. Super Eddington accretion opens the throttle. It gives black holes a way to grow faster than anyone thought possible within the classical framework. But feeding rate is only one variable in the equation. There's another variable that's equally important, maybe more important, and it comes not at the end of the growth story, but at the very beginning. The seed. The starting mass. The mass of the black hole on the day it was born. This matters because of how exponential growth works. When something grows exponentially, its final size depends enormously on where it started. Double the starting point and you double the final result at every moment along the way. A black hole that begins at 1,000 solar masses instead of 100 solar masses doesn't just arrive at its final size a little sooner. It arrives dramatically sooner. Every additional e-folding you can eliminate from the required growth, every factor of 2.7 you can shave off by starting heavier, translates directly into hundreds of millions of years saved. And in the early universe, where time is the scarcest resource of all, those saved years make the difference between a black hole that reaches 1 billion solar masses before the cosmos is 1 billion years old, and one that falls hopelessly short. So where do black hole seeds come from? What creates the first black holes in a universe that didn't previously contain any? The most straightforward answer is stars. The first generation of stars, called population 3 stars, formed from the pristine hydrogen and helium gas left over from the Big Bang. These stars contain no heavy elements, because heavy elements didn't exist yet. They hadn't been forged in stellar cores and scattered by supernovae. The gas was pure. And pure hydrogen-helium gas behaves differently from the enriched gas that forms stars today. It cools less efficiently, which means the collapsing gas clouds fragment less, which means the resulting stars tend to be larger, much larger. The first stars are thought to have been enormous by modern standards. While typical stars forming today have masses comparable to our Sun or smaller, population 3 stars likely ranged from tens to hundreds of solar masses. Some theoretical models suggest individual stars exceeding 200 or 300 solar masses. These were brilliant, furiously hot objects that burned through their nuclear fuel in just a few million years, a cosmological blink of an eye, before dying in catastrophic explosions or collapsing directly into black holes. When a massive star collapses, it can produce a black hole with a mass that's a substantial fraction of the original star's mass. A star of 200 solar masses might leave behind a black hole of 50 to 100 solar masses, depending on how much material gets ejected during the collapse. This is what astronomers call a light seed. Light not because it's lightweight in any human sense. 100 solar masses is still an extraordinary concentration of matter, but because it's light compared to the billion solar mass monsters it needs to become. And as we showed earlier, getting from 100 solar masses to 1 billion solar masses through Eddington limited accretion alone requires roughly 16 e-foldings over more than 700 million years of continuous feeding. That's incredibly tight. The timeline barely closes even under the most generous assumptions. And it fails entirely when you account for realistic interruptions in the gas supply. But what if the seed were heavier? What if, instead of starting at 100 solar masses, the black hole began its life at 10,000 or even 100,000 solar masses? that would slash the required growth dramatically. Going from 100,000 solar masses to 1 billion solar masses requires only about 9 E-foldings instead of 16. That cuts the required continuous feeding time nearly in half, from roughly 720 million years down to about 400 million. Suddenly, the timeline becomes comfortable rather than desperate. There's room for interruptions, room for quiet periods, room for the messy reality of galaxy evolution without jeopardizing the final result. The question is whether nature provides a mechanism for creating such heavy seeds. And remarkably, it might. The mechanism is called direct collapse, and it's one of the most dramatic ideas in modern astrophysics. Here's the concept. In the standard picture of star formation, a cloud of gas collapses under its own gravity. As it collapses, it heats up. The heated gas radiates energy, cools down, and continues collapsing. This cooling is essential. Without it, the rising pressure inside the cloud would halt the collapse before the gas became dense enough to form a star. The cloud would just sit there, hot and diffuse, supported by its own thermal pressure. Now, imagine a special environment in the early universe. A massive cloud of pristine gas, containing perhaps 100,000 or even 1 million solar masses. But crucially, this cloud has almost no molecular hydrogen. Molecular hydrogen is the primary coolant for primordial gas. It allows the gas to radiate away its thermal energy and collapse into dense clumps that form individual stars. Without molecular hydrogen, the gas cannot cool efficiently. It stays hot. The pressure stays high. And instead of fragmenting into many smaller clumps that each form individual stars, the entire massive cloud collapses monolithically. It falls inward as one enormous structure. What could destroy the molecular hydrogen? Intense ultraviolet radiation from nearby galaxies or star-forming regions. This radiation breaks apart molecular hydrogen molecules, robbing the gas cloud of its primary coolant. Without cooling, the gas follows a completely different evolutionary path, and this is where the scenario becomes truly extraordinary. The collapsing gas doesn't form a normal star. It forms what theorists call a supermassive star, an object containing tens of thousands or even 100,000 solar masses of material crammed into a single bloated structure. This supermassive star is unlike anything in the present-day universe. It's enormous in both mass and physical size, with a surface temperature that's surprisingly modest given the incredible amount of energy it generates. Its luminosity approaches or exceeds the Eddington limit for its own mass, meaning radiation pressure is barely holding it together from the moment it forms. And it doesn't last long. A supermassive star of this kind cannot sustain itself through nuclear fusion the way an ordinary star does. Nuclear fusion in its core produces energy, but the energy generation rate cannot keep pace with the radiative losses from such an enormous object. The star is thermally unstable. It burns through whatever equilibrium it manages to achieve in a cosmologically negligible span of time, perhaps a few 100,000 years, maybe 1 million at most, and then it collapses. Not with a supernova explosion that scatters most of the mass. The collapse is so complete, so overwhelming, that nearly all of the star's mass falls inward and forms a black hole. Very little is ejected. The result is a black hole containing nearly the full mass of the progenitor. A heavy seed. Born not at tens or hundreds of solar masses, but at 10,000 to 100,000 solar masses. A massive head start in the race to reach 1 billion. Direct collapse black holes are theoretically compelling, but they require very specific conditions. The gas cloud must be metal-free or nearly so, limiting this mechanism to the very early universe before heavy elements had been widely dispersed. The cloud must be bathed in exactly the right intensity of ultraviolet radiation, strong enough to destroy molecular hydrogen, but not so strong that it ionizes the gas and disrupts the collapse entirely. And the cloud must be massive enough and must avoid fragmenting despite the lack of cooling. These conditions are restrictive. Direct collapse black holes probably didn't form everywhere. They might have been quite rare, but they didn't need to be common. Even a small number of heavy seeds sprinkled across the early universe could account for the population of billion solar mass black holes observed at high redshift. The debate between light seeds and heavy seeds has been one of the central arguments in black hole astrophysics for over 2 decades. Light seed advocates point out that stellar mass black holes from population 3 stars are essentially guaranteed to form. We know massive stars exist. We know they produce black holes when they die. The mechanism is well understood. Heavy seed advocates counter that the timeline problem is nearly insurmountable with light seeds alone, even with super Eddington accretion. And that direct collapse provides a natural solution if the conditions are met. The truth, as usual in astrophysics, is probably a combination. The universe likely produced both light seeds and heavy seeds. The light seeds were more common but started smaller. The heavy seeds were rarer but started much larger. The black holes that grew into the earliest and most massive quasars might have been the lucky ones. The seeds that formed heavy found themselves in gas-rich environments and experienced multiple episodes of super Eddington feeding during the first billion years of cosmic history. But there's a third ingredient in the growth recipe that we haven't fully explored yet. Mergers. Black holes can grow not only by consuming gas, but also by colliding and combining with other black holes. And this mechanism, unlike accretion, doesn't depend on gas supply at all. It requires only that 2 black holes end up close enough together for gravity to bring them together. Galaxy mergers were extremely common in the early universe. The cosmos was denser, galaxies were closer together. Gravitational interactions between galaxies happened frequently. And when 2 galaxies merge, their central black holes don't immediately combine. Instead, they sink toward the center of the merged galaxy through a process called dynamical friction, gradually losing orbital energy to the surrounding stars and gas. Over millions of years, the 2 black holes spiral closer and closer until they form a gravitationally bound pair, orbiting each other at close range. From there, gravitational wave emission takes over, draining the remaining orbital energy and driving the black holes together in a final dramatic plunge. They merge, their masses add together, and the resulting black hole is more massive than either parent. We know this process happens because we have detected it directly. In 2015, the LIGO Gravitational Wave Observatory made the first direct detection of gravitational waves from a binary black hole merger, an event designated GGW 15914. 2 black holes, one about 36 solar masses and the other about 29, spiraled together and merged into a single black hole of about 62 solar masses. The missing 3 solar masses were radiated away as gravitational waves, ripples in the fabric of space-time that traveled across more than 1 billion light-years of space before reaching Earth. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of binary black hole mergers, and some of these detections have told surprising stories of their own. In 2019, LIGO detected an event designated GW190521 that involved two black holes significantly heavier than anything expected from standard stellar evolution. One weighed roughly 85 solar masses, and the other about 66. The merged remnant came in at approximately 142 solar masses, making it the first confirmed intermediate mass black hole ever detected. What made this event remarkable was that the component masses fell in what physicists call the pair instability mass gap, a range of masses between roughly 65 and 120 solar masses where conventional stellar collapse should not produce black holes. Stars in that mass range are expected to be completely destroyed by thermonuclear explosions during their deaths, leaving nothing behind. The existence of black holes inside this forbidden mass gap suggests that at least some of them were themselves the products of earlier mergers. A black hole of 85 solar masses might have been built by a previous collision between two smaller black holes, each in the 30 to 40 solar mass range. Those smaller black holes merged, producing a remnant heavy enough to fall inside the gap. Then that remnant found another partner and merged again, producing the event that LIGO detected. This kind of hierarchical merging, where the products of one merger become the ingredients for the next, can build up mass step by step without any gas accretion at all. Now, scale this process up to the early universe. Young galaxies merged frequently. Each galaxy might have contained one or more black holes from the first generation of stellar collapses, or perhaps a direct collapse heavy seed at its center. When these galaxies merged, their black holes eventually merged too. A sequence of hierarchical mergers, small black holes combining to form medium ones combining to form large ones, could build up significant mass over cosmic time. A series of 5 or 6 doublings through mergers can take 100 solar mass seed to several thousand solar masses. That alone doesn't reach 1 billion, but it provides a substantial boost that reduces the amount of accretion needed to finish the job. In practice, mergers and accretion probably worked in tandem. Galaxy mergers didn't just bring black holes together, they also drove large quantities of gas toward the center of the merged galaxy, fueling bursts of intense accretion. So a typical growth episode might look something like this. Two galaxies collide. Gas flows inward, triggering a super Eddington feeding burst. The two central black holes spiral together and eventually merge. The newly combined, more massive black hole sits at the center of a gas-rich merged galaxy and continues feeding. The mass increases through both channels simultaneously, through the additive jump of the merger event and through the continuous growth of super Eddington accretion fueled by the merger-driven gas inflow. Let me paint a more concrete picture of what this combined growth story might actually look like, from start to finish, for a single black hole across the first billion years of cosmic history. Imagine the universe roughly 150 million years after the Big Bang. The first stars have formed in small pockets of dense gas scattered through the cosmic web. One of these stars, a massive population 3 behemoth containing perhaps 200 solar masses, burns through its hydrogen fuel in barely 3 million years. It collapses, producing a black hole of roughly 80 solar masses, a light seed. Small, newly born, sitting in a tiny protogalaxy containing only a few million solar masses of gas and stars. For tens of millions of years, this seed grows slowly. Gas trickles inward, feeding the black hole at a modest fraction of its Eddington rate. The black hole doubles its mass once, twice. It reaches a few hundred solar masses, not fast enough. At this rate, it would take billions of years to reach supermassive territory. But then, something changes. Nearby, in a neighboring region of the cosmic web, a massive cloud of pristine gas has been bathed in ultraviolet radiation from the growing population of young galaxies. The molecular hydrogen in this cloud has been destroyed. The cloud collapses monolithically, forming a supermassive star that quickly collapses into a direct collapse black hole of 50,000 solar masses. A heavy seed. It sits in its own small protogalaxy, waiting. Around 300 million years after the Big Bang, the two protogalaxies begin to interact gravitationally. They're close enough that the pull is significant. Over tens of millions of years, they fall together and merge. The collision drives enormous quantities of gas toward the center of the newly combined galaxy. Both black holes, the light seed now at a few hundred solar masses and the heavy seed at 50,000, begin spiraling toward the center. The heavy seed, being much more massive, sinks faster. Gas piles up around it. The accretion rate surges. For the first time, the heavy seed enters a super Eddington phase, feeding at perhaps 10 or 20 times its Eddington rate. In just a few million years of intense feeding, it doubles its mass, then doubles again. It reaches several 100,000 solar masses. Meanwhile, the smaller black hole is still spiraling inward. After another 50 million years of dynamical friction, the two black holes find each other. They form a binary pair, orbiting each other at increasingly close range. Gravitational waves drain the remaining orbital energy. They merge. The combined black hole now contains several 100,000 solar masses, the vast majority contributed by the heavy seed and its super Eddington growth. This pattern repeats. Other small galaxies fall in. Each merger drives fresh gas inward, triggering another super Eddington burst. Each burst adds mass. Some merging galaxies bring their own black holes, which eventually merge with a growing central object. By 500 million years after the Big Bang, the black hole has reached 10 million solar masses. By 700 million years, through a combination of several major mergers, multiple super Eddington feeding episodes, and steady background accretion during quieter intervals, it has crossed 100 million solar masses. One final major galaxy merger, bringing a fresh supply of cold gas, and one more companion black hole, pushes the accretion rate to its most extreme level yet. For perhaps 10 million years, the black hole feeds at 30 or 40 times its Eddington rate. It crosses the billion solar mass threshold. It shines as a brilliant quasar, visible across the observable universe, its light destined to travel for more than 12 billion years before reaching a telescope on a small planet orbiting an unremarkable star in a spiral galaxy called the Milky Way. This narrative is hypothetical. No astronomer has tracked a single black hole across its entire growth history. The details would vary from object to object. Some black holes might grow primarily through accretion, with relatively few mergers. Others might experience many mergers, but fewer extreme feeding episodes. The relative importance of each mechanism probably differs from case to case, but the overall picture, heavy seeds gaining mass through bursts of rapid accretion, punctuated by merger events that both add mass directly and replenish the fuel supply, is the framework that best explains what we observe. This combined picture, heavy seeds plus episodic super Eddington accretion plus hierarchical mergers, represents the current best understanding of how the earliest supermassive black holes came to be. No single mechanism is sufficient on its own, but together, with each mechanism contributing what it does best, the growth becomes achievable. The James Webb Space Telescope is now providing the observational data needed to test this picture. Since beginning science operations in 2022, it has peered deeper into the early universe than any previous telescope. And the results have been both confirming and challenging. On the confirming side, the James Webb Space Telescope has discovered numerous galaxies at very high redshifts, hosting active black holes. Some of these black holes appear to be growing rapidly, consistent with super Eddington or near Eddington accretion. The fact that so many active black holes are being found in the first billion years of cosmic history supports the idea that rapid feeding was widespread during this epoch. On the challenging side, some of the galaxies discovered by the James Webb Space Telescope are more massive and more evolved than expected at such early cosmic times. They contain more stars and more structure than models predicted. This suggests that not just black holes, but galaxies as a whole were growing faster in the early universe than our standard models assumed. The entire cosmic assembly process, the building of structure from primordial gas, may have been more efficient, more rapid, and more extreme than we thought. Super Eddington accretion onto black holes might be just one manifestation of a broader theme. The early universe was a more intense, more productive, more extreme environment than the orderly cosmos we observe around us today. There's an object discovered through joint X-ray and James Webb Space Telescope observations, designated UHZ1, that beautifully illustrates the interplay between seeds, growth, and environment. This black hole was found in a galaxy at extremely high redshift, embedded within the early stages of galaxy cluster formation. The surrounding environment is dense with gas and neighboring galaxies, exactly the kind of setting where heavy seeds might form, and where both mergers and gas-fueled accretion could proceed rapidly. The black hole appears to have a mass comparable to its host galaxy's stellar mass, which is highly unusual by present-day standards. In the nearby universe, central black holes typically contain only about 0.1% of their host galaxy's mass. UHZ1's black hole appears to make up a much larger fraction, suggesting it grew disproportionately fast relative to the galaxy around it. This is consistent with either a very heavy seed, extremely rapid accretion, or both. Another intriguing case involves the galaxy GNZ11, one of the most distant galaxies known. Spectroscopic observations have revealed signatures suggesting the presence of an actively feeding black hole at its center. This galaxy existed when the universe was only about 400 million years old. Finding an active black hole at such an early cosmic time puts extreme pressure on any growth model. Even with heavy seeds and super Eddington feeding, building a supermassive black hole in just 400 million years is an extraordinary challenge. Objects like GNZ11 are pushing the boundaries of what our models can explain, and forcing theorists to consider whether the conditions in the very early universe were even more extreme than current simulations suggest. There is much that remains unknown. We don't know how common direct collapse black holes actually were. We don't know the typical duty cycle of super Eddington episodes, how often they occur, how long they last, or how extreme they typically get. We don't know the precise merger history of early black holes. We don't even know whether there might be additional seed formation mechanisms that nobody has thought of yet. Some theorists have proposed that dense nuclear star clusters in early galaxies might have produced intermediate mass black holes through runaway stellar collisions, creating seeds of a few thousand solar masses through a pathway completely different from either stellar collapse or direct collapse. Future observations will help constrain these uncertainties. The planned LEESA mission, a space-based gravitational wave observatory expected to launch in the 2030s, will detect mergers between massive black holes, the kind that involve thousands to millions of solar masses. These are precisely the mergers that build supermassive black holes during the era of galaxy assembly. LIGO and similar ground-based detectors observe stellar mass mergers. LEESA will observe the heavyweight collisions, the mergers that no electromagnetic telescope can detect because they may occur in gas-poor environments or at distances too great for light-based observations to resolve. LEESA will tell us how frequently massive black holes merged in the early universe, what mass ranges were involved, and how much those mergers contributed to the overall growth of the supermassive black hole population. Combined with continued observations from the James Webb Space Telescope and future X-ray observatories, LEESA will provide the data needed to finally distinguish between competing growth scenarios. Do most supermassive black holes grow primarily through gas accretion, or do mergers play an equal or even dominant role? Were heavy seeds essential, or could light seeds with enough super Eddington feeding do the job alone? These questions have been debated theoretically for decades. Within the next 10 to 20 years, we may finally have the observational evidence to answer them. Let's step back now and think about what all of this means in a broader sense, because the story we've told tonight is about much more than just black holes. It's about the nature of limits, about the difference between a fundamental law and a convenient approximation, about how the universe finds ways to build complexity and structure under conditions that seem, at first glance, to forbid it. The Eddington limit was never wrong. It was always a valid calculation under the assumptions it was built on. But those assumptions described an idealized situation, a spherically symmetric, steady state, thin disk accretion flow that obeyed a specific set of rules. The real universe is not obligated to follow those rules. Gas doesn't fall in spherically. Disks aren't always thin. Radiation doesn't always escape cleanly. And when conditions become extreme enough, the tidy theoretical picture breaks down. The limit isn't violated. It's circumvented. The universe doesn't break the law. It finds a loophole. There's something deeply instructive about this. In physics, the things we call limits are often more subtle than they first appear. The speed of light really is an absolute limit. Nothing with mass can reach it, and nothing at all can exceed it. That limit is woven into the structure of space-time itself. But the Eddington limit is different. It's an emergent property of a specific physical configuration, not a fundamental constant of nature. Change the configuration and the limit changes with it. Push the configuration far enough from the assumed ideal and the limit stops applying altogether. Recognizing which limits are truly fundamental and which are merely conventional is one of the great ongoing challenges of physics. And the story of super Eddington accretion is a beautiful example of how that distinction plays out in practice. It also speaks to the universe's remarkable ability to build structure rapidly when conditions demand it. The early universe was a violent, chaotic, gas-rich environment. Galaxies were colliding, gas was flowing inward, black holes were forming, feeding and merging at rates that would be extraordinary by the standards of the calm, orderly cosmos we inhabit today. And out of that chaos emerged the seeds of everything we see around us. The supermassive black holes at the centers of galaxies, the galaxies themselves, the large-scale structure of clusters and filaments, all of it traces back to processes that occurred in the first billion years, processes that included episodes of feeding so extreme they seemed to defy the physics that was supposed to govern them. There is something humbling about this realization, something that extends beyond astrophysics into how we think about knowledge itself. For decades, some of the most brilliant minds in science looked at the Eddington limit and saw a wall, a firm boundary, a rule that couldn't be broken. And they were right about the physics. The calculation was correct. The predictions matched observations. Everything checked out. But they were wrong about the scope of those predictions. They assumed the idealized conditions would always hold. They didn't anticipate that nature, under extreme enough pressure, would find configurations so far outside the assumptions that the limit would simply cease to apply. This happens again and again in the history of science. We discover a rule, we test it, it works, we trust it, and then the universe shows us a corner of itself where the rule was never the right rule to begin with. Not because the physics changed, but because the conditions changed. The lesson isn't that science gets things wrong. The lesson is that every scientific result has a domain of validity, and nature is very creative about finding conditions outside that domain. When you look up at the night sky tonight, every galaxy you can see, whether with your naked eye or through a telescope, hosts a supermassive black hole at its center. Those black holes didn't simply appear, they were built. Built from seeds, grown through gas, merged through collisions, shaped by the same physical laws that govern everything in the cosmos. And some of them grew faster than anyone thought possible, exploiting loopholes in a limit that turned out to be more flexible than generations of astrophysicists assumed. The question we started with tonight was simple. How can a black hole grow faster than physics should allow? And the answer, as it turns out, is that physics does allow it. The ceiling was never as firm as it appeared. Under the right conditions, with the right geometry, with enough gas and enough density and enough chaos, black holes can shatter the classical speed limit and grow at rates that once seemed impossible, not by breaking any law, but by operating under conditions where the simple version of the law simply doesn't apply. The Eddington limit isn't a wall, it's a fence built for a specific landscape. Change the landscape, and the fence no longer stands where you expect it to. The universe changed the landscape, and the black holes grew